Hi, I'm Pang Wenjun, and I'll talk about optical devices. Uh, Optical devices operate like a light, so observing light or um, emission of light, something. So, if observing lights and creates current and voltage, and when it um, voltage to optical devices, and it can emission some light. So this is the operation of the um, optical devices. So this is the energy band and this is the conduction band. If it's is an electron is on the valence band, but if lights is in light is on there on this electron, and it can go up. So and light can have to more than bigger than have energy bigger than its energy gap. Okay, and if electron on the conduction band and it goes down uh, spontaneously, and emission of the light, and this lights will be have energy exactly what this is the energy gap. And when an electron is on the conduction band and lights can hit the electron and goes down and emission light, and it can be it will be emission light exact too. Okay, so um this is the what they said. So h is the Planck constant and v is the frequency. So this is the what is that, and it can calculate by this approximately this. So if lambda is 400 nanometer, and it energy will be 3 point something electron. Okay, and its material optical devices material is usually use 3,5 materials like gallium arsenide. Okay. mm, and it when light goes in to the device, and it faces the surface, and some of the lights can will be reflection. So this is the reflection efficiency. So R is n minus n2 over n1 plus n2 square. N1 is the reflection constant of the device 1, something device 1, and device 2 of the reflection is N2. For example, air is 1 reflection constant. Okay, reflective index. Okay, and transmission coefficient is the um, remain of the reflect, and it's remain something, so it's 1 minus r. Generic photo device. Okay, um when lights through the device, and it will be absorb absorb energy and um, goes down. So it's alpha. This is the observed. This is alpha. Alpha is reflective coefficient. So here's like this. So lights go in there, and something is reflective, and reflect and remain lights will be through the device, and it will be alpha is like this. Very alpha is more bigger, and stiff is very shallow, and 1 over alpha is the um, light's mass will be 37 point of the that point, like that here, like here like this. And energy gap, we said about energy EK diagram, and semiconductor is very typical indirect band gap, have a indirect band gap, and 3-5 materials are usually direct band gap, like this. So when electron gets energy of the over the energy gap and goes up easy, but when semiconductor electron when electron goes up, it have to more than electron gap plus delta K is the 운동량 영어로 뭐지? 운동량 amount of exercise. It's like that. So and this is the graph of the alpha observation coefficient and energy Poisson energy. So it goes up, it will be more energy, and more up, and have more alpha is bigger. Okay, so blue dot line is indirect material, and it goes here like this, something have a degree, and direct material is like this black line. It have like a very steep. So it says direct band gap material is more have more alpha. So absorption coefficient. Okay, and for diode basic, diodes have the depletion region in neutral but non-bias condition, and when lights go to the face the hit the diode, and neutral region and depletion region both have generated whole pair, but in neutral region whole pair is it can be ignored because it doesn't matter. But in here in depletion region, whole pair have to drift, they drift because of the electric field in the depletion region because of the fixed charge. And so this makes a current. So uh, depletion region will when depletion region is bigger, larger, and current is more larger because of the uh, more generate whole pair. And if and when reverse bias in diodes, and it can be it makes more it makes larger depletion region. So uh, and current will be reverse uh, reverse 방향이 기억나네. Direction. Reverse direction. Current will be reverse direction. Okay. Whole plus bias is here, so minus electron is here, and plus is here. Whereas whole is here, so current is here, and this is the reverse direction. And when reverse direction, reverse bias more larger, and current will be more little bit like a more larger. Okay, larger current will be generated. So this is the graph, and when current is 0 and these points are open circuit voltage, and when voltage is 0, and this will be short circuit current. Okay, and solar cell, like a solar cell, dark, no light current. So this is current, dark current is like this, very exponential something, and I total is dark current, and when lights hit the device, and they makes current. So light current and dark current plus is the current, total current. Okay, and there is a quantum efficiency. This is the flux in the device when have something, and how many current will be generated is the quantum efficiency, and responsibility is the RPF, pH, and this is the how many photon power, how many current related to how many photon power. Okay. And this is the fill factor. This is the how many this is like a something efficiency factor. Okay, so like real max power over the ideal power max. Okay, so this is the graph of the IV curve of the photon device, and here violet area is the real power max. So, and here open circuit voltage and short circuit current will be phased to here, and it will be made a ideal max power. So So F is the I max V max over short circuit current and open circuit voltage, and it will be something 0.7. Okay. And continuity equation. Okay. When junction made about P and N, and it can made depletion region, and this is P plus. So N semiconductor region has larger depletion region than P depletion region. Okay. And okay, so we said before, so larger depletion region can make more current. So this is the same thing, but this is related to lifetime carrier lifetime. So exactly, um, minority carrier time lifetime, and G is the constant, and PIN diode is the something solution of the how 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 we made more depletion region. So this is the P and intrinsic and N semiconductor. So when when reverse bias on the PIN diode, and intrinsic area will be become a depletion region, and so we can make more larger depletion region, and we can made more efficiency photon divide. And this is the LED. LED is the four device and diodes, and we put the LED of forward bias, and electron and hole is something like through the each depletion region, and when it go through the depletion region, and it can face the hole in electron, so they can regeneration. Oh, no. 합쳐지다. Oh, recombination. Okay, recombination. They can recombination. So, but they when forward bias very large or depletion is very short or something, time and throwing time will be when short, and facing time is very short. So recombination efficiency is very low. So we have to more have more recombination of the carrier. So we made something sink of the here. So when electrons go to forward bias, so go to up, and goes down and sink to here, and hole is two, so they sink of here, and they can recombination. We have more recombination, and we made more efficiency LED. And this is the OLED. O is organic, so OLED is made by carbon, So this is not crystalline. This is like a polymer. So its advantage is like this, very smooth and flexible, and it made very easy. This can be made very easy to make. So, and this is the Lumo. This is not the crystalline, so they have very many in the energy band, but lowest band of the here is the Lumo. This is like the conduction band, and HOMO is like a work like a valence band. So when goes here and goes down, something like that, and generating light. Um, and this base will can make this base can be a polymer, so we can use very flexible, okay, like a flip phone or fold phone, and something like a wristband, like a something very useful device is the OLED. Thank you. That's all.